Hello, this is the second part of the chapter 5.4, and we will talk about the matrix of linear transformation from any dimensional space to another any dimensional space. Let me remind you that any linear transformation from n-dimensional to m-dimensional space can be implemented by left multiplication by a matrix A. And we call this matrix the standard matrix of transformation T. So, okay, let's look at the transformation T. And let's say this is a linear transformation from Rn to Rm. And let's say that Rn is our v-dimensional space. Oh, that our v is n-dimensional space, like there is an image of it over here. And there is x, which is belong to this n-dimensional space. It can be any vector. We know that we always can go from v to our n-dimensional space Rn. And this Rn will have a basis, some kind of basis, which always has to consist of n vectors. We call it from b1 to bn. And we can write down our vector b in the coordinates of this basis. So we will call this xb is our coordinate vector. And it will consist of just n number, and we'll number them from R1 to Rn. But important thing to remember, those are just numbers. Okay, so now we will apply the linear transformation and go from the space V to the space W. And we will create the image of our space after our vector x, and we'll call it T of x. And of course, again, we always can go from our space W to the similar dimensional space Rm. So then we will express our image T of x in the coordinate vectors of our m-dimensional space. So it will be a different basis. It will consist of m vectors. So the question is, how can we go from our Rn to Rm directly? So if we are only given the transformation between V and W. Okay, let's start thinking about it. So we know that we have our vector x, which written in the basis b. We can then write down our original vector x using this basis and the coordinates as a linear combination. R1, B1 plus all numbers until we reach Rn and Bn. Okay, so now, since we have a vector x now, let's just apply our transformation 2 to the vector x. And because our transformation is a linear one, we can break down this sum into the sum of the transformations. We also can pull out constant R1 and Rn, they're just numbers, and then multiply each of the transformation by a constant. So what will we get at the end is the linear combination of our coordinates R1 and Rn and images of our basis vectors from B1 to Bn. So we can write it down as the product of matrix, which just consists of images of our basis vectors, and we will call it matrix M. And the long name for matrix M is a matrix for T transformation T relative to the bases B and C. And this matrix will multiply by our coordinate vector in B, which is just a set of numbers from 1 to Rn. So what we found here is the easy way to go from Rn to Rm directly. We can write down the image of our vector x in coordinate C as the product of matrix of transformation times our vector x in coordinates B. And of course, our matrix M will consist just the images of our basis vector. So, and this is the shortcut for us to move from Rn to Rm directly instead of going between the V and W. Okay, so let's just try to practice a little. And by the way, we don't have to always calculate our coordinates of our image. We might be already given the coordinate of image and we just need the matrix of transformation. Like in this example, for example, we are given the basics in two-dimensional space R2 and the basis vectors are B1 and B2. We also are given three vectors C1, C2, and C3, which form a basis in our three-dimensional space W. And we also given a linear transformation. And we are also given images of our basis vectors in our three-dimensional space. So now, given all this information, can we find the matrix M for the T relative to the bases B and C? Okay, let's start thinking about it. So here, clearly, we are already given the coordinates of our image, T of X. So we have two images of two basic vectors. We are knowing that our vectors in the basis vectors in B. All we need to find is the matrix of transformation. So let's just start by writing down the coordinate for our images of our basic vectors in the coordinates of C, which will be for the T of B1, that would be just our weights in front of the basis vectors C1, C2, and C3. So it will be a vector from the first component will give us 3, second component give us -2, and the third component will give us 5. Okay, so let's look at the second image of second basic vectors. Again, in the coordinate systems of our vector space C, again, we can compile them from the weights in front of the parameter C in our equation for the image. So the first will give us 4. The multiplier in front of C2 will give us a second component of the vector, and multiplier -1 in front of C3 will give us -1. Okay, so let's look at our original formula. So the matrix M is actually consists of the column of the vectors, basic vectors of B written in coordinates C. So all we have to do is actually take these basic vectors and just compile them into the matrix. And that matrix will be our matrix M for the transformation. Okay, this is a little bit abstract example, but we're talking about very highly dimensional space. So for next time, we will talk how to work with the similarly dimensional spaces.